Good morning, students. In the last class we saw about the vibrations of monoatomic and the diatomic atoms in the one-dimensional space. Today we will discuss the topic about specific heat capacity and the lattice vibrations. You all know what do you mean by specific heat capacity and lattice vibration. Specific heat capacity is nothing but the amount of heat energy required to heat 1 gram of a substance through 1 degree Celsius. Also, there are two types of specific heat capacities. One is specific heat capacity at constant volume and specific heat capacity at constant pressure. That is, both are represented as CV and CP. We also studied about Meyer's relation, CP minus CV is equal to R. These are all comes under the topic kinetic theory of gases. These specific capacities contribute various factors. One is the atomic vibration in the crystal, another one is the electronic contribution. In the atomic vibration in the crystal, when we are giving the heat energy as the input for the solid, the atoms in the solid will accept that heat energy and its temperature increases. As the temperature increases, the atoms vibrate more accordingly on the basis of the temperature. So this is happening in atomic vibration in the crystal. We know atoms consisting of electrons, protons and neutrons. These vibrations will be due to electronic contribution also. This mostly happens in semiconductors and in metals. But this electronic contribution energy will be small as compared to that of atomic vibration and the lattice vibrations. Okay, so by atoms, by giving the heat energy, it will vibrate. Another one is in semiconductors and metals, due to electronic contribution, the vibration will take place. Okay, right. The important law according to this specific capacity is Dulong and Petit's law, was proposed in the year 1890. According to them, the molar specific capacity of many solid substances is about 3R, where R is the universal gas constant. That is, the specific capacity of many solid substances is about 3R, where R is the universal gas constant. Its value is 25 joules per Kelvin. That is, according to Dulong and Petit's law, they proposed that the specific heat capacity of crystals per mole gram of atoms they contain. It represents the crystals per mole atoms they contain. According to classical theory of specific heat capacity, they had these following assumptions. What are the assumptions? Each solid consists of number of atomic particles, number of atomic, not articles, these are number of atomic particles, okay, number of atomic particles executing simple harmonic motion about the equilibrium sites. They are called as atomic oscillators. Okay, all the solids having the atoms of individual particles, and each atomic particle will vibrate simple harmonic motion, hence they are called as atomic oscillators. This is the first assumption. These atomic oscillators vibrate with the same frequency, but their energies are different. Same frequency, but energies are different because they vibrate with different amplitudes. Okay, it is the second assumption. Then the inter energy is largely contributed due to vibration energy only. Due to vibration only, these energies are created, and it will create mostly the contribution of the total energy. Okay, so there are atoms in the solid. These atoms will vibrate and it is called as atomic vibration or atomic oscillators, and these atomic oscillators vibrate with the same frequency but different energy due to their different amplitudes. Most of the energy is due to vibration energy of all atomic oscillators. There will be no restriction of the energy of this atomic oscillator. Its value ranges from 0 to infinity. Its value ranges from 0 to infinity. The total energy of the crystal given temperature is n times the average energy E of the oscillator. So what will be the total energy of the crystal at a given temperature? It should be n times the average energy E of the oscillator. N means number of atoms. So if there are 100 atoms, 100 into average energy. If there are 1000 atoms, 1000 times the average energy. It will be the total energy of the crystal. So these are the basic assumptions in the classical theory of specific heat capacity. What will be its approach? According to classical approach, the energy of the harmonic oscillator is total energy is equal to kinetic energy plus potential energy. Kinetic energy plus potential energy. We know. Then kinetic energy is nothing but P square by 2m. Potential energy is nothing but m omega square x square by 2. By combination, it is the total energy. You see here, this is the total energy, that is E is equal to P square by 2m plus m omega square x square by 2, where P is the momentum, omega is the angular frequency of the oscillator, x is the displacement from the mean position, and m is the mass of that atom. So this is the total energy formula. E is equal to P square by 2m plus m omega square x square divided by 2. The average energy of the harmonic oscillator according to classical statistical mechanics is total energy E is equal to total energy of the occupied state divided by the total number of occupied states. Total energy of the occupied states divided by the total number of occupied states. So, as E is equal to integral 0 to infinity, because we already told it ranges from 0 to infinity. Therefore, integral 0 to infinity e power minus E by kt into dou E divided by integral 0 to infinity E power minus E by kt into dou E. There is the only difference is E only. Okay, so this is the total energy of the occupied states and this is the total number of states. Okay, so this is the difference. This difference gives the total energy. It should be approximately equal to kT, where k is the Boltzmann constant, T is the absolute temperature. So when you are multiplying this k and t, you will get the average energy of the harmonic oscillator. Okay. If there are n number of oscillations takes place, there is n number of atoms, each n atoms will vibrate. Therefore, if there are n number of atoms, according to vibrational energy, 3n oscillations are allowed. X direction, Y direction, Z direction. Therefore, there will be 3 directions are possible. Therefore, for one atom, there will be 3 directions. Therefore, it is written as 3n kT. E is equal to 3n kT. This is independent of the frequency of the oscillator and depends only on the temperature. Depends only on the temperature. Then we find out this energy. Then what is CV? Differentiation with respect to time will give, differentiation of energy with respect to time will give the specific capacity at constant volume. Therefore, formula is CV is equal to dou E by dou T. E is equal to 3n by kT. When you are differentiating this, you will get 3nk, but this nk is nothing but R, universal gas constant R. Therefore, Cv is equal to 3R. We already studied in Dulong and Petit's law, most of the solids will give the value of 3R. Specific capacity will be 3R. So this is the classical approach. Have you understand these things? Okay. So we had some assumptions. According to these assumptions, the total energy should be is equal to this equation number 2. From that, we are integrating the things and we are finding out Cv by dou E by dou T. So this is 3R. Cv is equal to dou E by dou T, that is equal to 3R. Now, in these specific heat capacity theories, there are two main theories are there. One is Einstein's theory of specific capacity and another one is Debye's theory of specific heat capacity. According to Dulong and Petit's law, most of the solids are having the specific heat capacity approximately equal to 3R. Then why these theories came? Einstein's theory and Debye's theory. This Einstein's theory is the first theory. It will adopted quantum mechanical approach than the classical approach. So Einstein's model is the first model adopted the quantum mechanical approach than classical approach. Why? So according to classical mechanics, classical theory or classical mechanics, classical approach, according to Dulong and Petit's law, it is equal to 3R. But at low temperatures, the specific heat capacity works differently. So in order to find out this behavior of specific heat capacity of solids in low temperature, this model was introduced by Einstein. So main aim is to find out the specific heat capacity behavior at low temperature of solids. But Dulong and Petit's law does not give the details about the low temperature of solids. Therefore, a new model was approached by Einstein according to quantum mechanical approach. So, Einstein model was adopted, quantum mechanical approach, to overcome the limitations of classical approach to explain the low temperature behavior of specific heat capacity. Einstein's model being the first shift from the classical to quantum prescription. Classical to quantum prescription. It is in this approach, a crystal of n atoms is assumed to be equal to 3n harmonic oscillators, but with same frequency mu. So, in this approach, the n atoms is assumed to be equal to 3n harmonic oscillators, but with the same frequency. Here, due to identical environment, the atoms were assumed to vibrate with the same frequency, but independent of each other. Vibrate with the same frequency, but independent of each other. So these are the two main things in the Einstein's theory of specific heat capacity. So Einstein's theory was introduced in order to explain the low temperature behavior of specific heat capacities. These models used quantum approach. According to this approach, n atoms is assumed to be equal to 3n harmonic oscillators, each vibrate with same frequency mu, but independent of each other. So this is the assumption by Einstein's theory of specific heat capacity. Okay. Now, since it is 3n harmonic oscillator, the values are quantized. This will be quantized energy equal to NH nu. NH nu. Where h is the Planck's constant, nu is the frequency, and n is an integer. It is the value takes from 0, 1, 2, 3, etc., etc. Okay, so Einstein approached the quantum mechanical expression of the energy of the harmonic oscillator in Planck in 1900 showed that harmonic oscillator does not have continuous energy spectrum like the assumptions made in classical mechanics. So in quantum mechanics, what is the difference in classical mechanics and quantum mechanics is, in classical mechanics they told it is the continuous energy spectrum, but according to Planck, harmonic oscillator does not have continuous energy spectrum, hence they are quantized energy levels called NH nu. So En is equal to here NH nu. E1 is the first energy, therefore 1h nu. If E1 is the second state, then 2h nu. If energy for third state, then 3h nu, etc. Now, the average energy, what will be the formula? E is equal to summation of n is equal to 0 to infinity NH nu e power minus h nu by kt divided by summation of n is equal to 0 to infinity e power minus nh nu by kt. So, what is the difference here in classical and quantum approach? In classical approach, there will be no summation, but in quantum approach, there is the summation of energies will takes place. And instead of E, they changed in the place E, they changed NH nu. This is the difference. Okay, in classical approach, delta E, that is total energy should be is equal to integral 0 to infinity E into e power minus e by kt divided by integral 0 to infinity e power e minus e by kt. This is in the classical. But in the case of quantum, instead of E, just you substitute NH nu. Also, this is not continuous energy spectrum in quantum mechanics. Summation will be introduced. Therefore, summation of n is equal to 0 to infinity NH nu e power minus NH nu by kt whole divided by summation of n is equal to 0 to infinity e power minus NH nu by kt. Okay, are you understand this formula? Now, you just take the denominator. The denominator is nothing but e power n is equal to 0 to infinity e power minus NH nu by kt. This should be written as, when you are expanding this series, you should be written as 1 plus e power minus h nu by kt plus e power minus 2h nu by kt, etc. It should be approximately equal to, this is the series value, that is 1 minus e power minus h nu by kt minus 1. Otherwise, in some books it will be written as 1 divided by e power minus h nu by kt minus 1. Some books it will be written as like that, e power minus h nu by kt minus 1. Not minus 1, h nu by kt. When it is goes up, then it should be written as like this. So, E summation of n is equal to 0 to infinity e power minus h nu by kt should be written as like this, 1 minus e power minus h nu by kt minus 1. Now differentiate this equation. Left side of this equation. What will be the left side? By 1 by kt. Okay, by 1 by kt. Therefore, dou 1 by kt of summation of n is equal to 0 e power minus nh nu by kt. When you are differentiating these things, e power something into something derivative. Therefore, this value comes like this. Okay. Then differentiate the right side with respect to 1 by kt. Then its value is minus 1. If you are taking it is x, then x power n. So n into x power n minus 1. Therefore minus 1 it will become minus 2. This minus term will come. This is for first term. Another e power something. Therefore minus e h nu by kt into something derivative. Therefore minus h nu. When you solve this minus whole minus. Then h nu, this e power minus h nu by kt divided by this term will come to denominator. Therefore minus 2 becomes plus 2. Therefore this is the equation. Okay, minus h nu e power minus h nu by kt whole divided by 1 minus e power minus h nu by kt the whole square. Okay, these equations are very easy. You just follow my notes, and when you are solving these equations by own, it will become. If you have any doubt, you ask me. Okay, right. Now you differentiate, equating the RHS of the equation 4 and 5. Both you equate it, then you will get this result. Okay, yeah. Now what will be the equation 2 becomes? Equation 2 we know, integral 0 to infinity e power minus e by kt whole divided by, that is the equation 2. That equation now becomes e is equal to, okay, e is equal to, you substitute this value, and you substitute this value as usual. When you solve this, you get e is equal to h nu e power minus h nu by kt whole divided by 1 minus e power minus h nu by kt. Okay, you just solve it and you will get easy. These are all easy things. Now you see, dividing the numerator and denominator by e power minus h nu by kt for my convenience. Therefore then it will go e is equal to h nu divided by e power h nu by kt minus 1. This is the average energy of the harmonic oscillator, and this equation is nothing but Planck's formula, Planck's equation. This equation is nothing but Planck's equation at a temperature T. Okay, right. Now, but we know that 3n of E, normally it is 3n of E, therefore E is equal to 3n into, substitute this value here, h nu divided by e power h nu by kt minus 1. So E is equal to h nu divided by e power h nu by kt minus 1, which is nothing but the Planck's law. According to quantum approach, total energy should be is equal to 3n times the energy. Therefore h nu divided by e power h nu by kt into 3n. Now we found the value of energy. Then from that value of energy, how can we calculate the specific heat capacity? Dou E by dou T. Differentiation of that energy with respect to temperature will give specific heat capacity. This is the basic law. So now you simply substitute Cv is equal to dou E by dou T. Therefore dou by dou T of 3n into h nu by kt. Here 3n h nu are all constant. You take out dou by dou T of e power minus h nu by kt minus 1. This term will go up, means it is minus 1. You simply differentiate it and you will get Cv is equal to this value, or Cv, that is equal to 3nk h nu by kt the whole square e power h nu by kt into e power h nu by kt minus 1. Instead of this nk, you substitute r. Okay, therefore Cv, that is equal to 3r h nu by kt the whole square e power h nu by kt e power h nu by kt minus 1 the whole square. Are you understand this equation? So we finally get Cv is equal to 3r h nu by kt the whole square e power h nu by kt whole divided by e power h nu by kt minus 1 the whole square. You mark up this equation 12. So you should remember what are the steps you are leaving. It is not the case, but final derivation is this is the derivation. Cv is equal to 3r h nu by kt the whole square e h nu by kt whole divided by e power h nu by kt minus 1 the whole square. This is represented by the equation 12. You just understand the things. Okay. Now, average energy according to the harmonic oscillator En is equal to n plus half h nu. We know these things in quantum mechanics also. N plus half h nu. Therefore, including the 0 point energy in the equation 9, what will be the equation 9? We know equation 9 is nothing but E is equal to h nu divided by e power h nu by kt minus 1. With that, we are adding the 0 point energy also, because when an oscillator is oscillating according to quantum mechanics, this harmonic oscillator has the minimum energy in the ground state, which is called as 0 point energy. Its value is equal to h nu by 2. We know the things. Okay, in quantum mechanics also we studied these things. When t is equal to 0, even though in the ground state temperature is equal to 0, its value should be equal to h nu by 2, which is nothing but what will be the average energy, which is called as 0 point energy. Here also the same thing happens. At t is equal to 0, this will come. Therefore, the only value will come is h nu by 2. Here h nu by v, if you change it as h nu by 2. Okay, so the average energy should be h nu by 2. So when t is equal to 0, as usual, you are getting the minimum energy called 0 point energy h nu by 2. Okay, so this is the first case. Now, at high temperature, what happens? That is, kT is very much greater than h nu. KT is very much greater than h nu. We know the equation 12. Equation 12, you see, Cv is equal to 3r into h nu by kt the whole square e power h nu by kt divided by e power h nu by kt minus 1 the whole square. Okay, so this is equation 12. Here, when kt is very much greater than h nu, kt is very much greater than h nu, then these all things will becomes 1. Therefore, Cv is equal to 3r only it will come. 3r. So when kT is very much greater than h nu, then this equation 12, Cv is equal to 3r only comes. Okay, which is nothing but classical approach. In classical approach also, all the solids will come with 3r. Specific capacity value should be is equal to 3r. So that 3r will come. Now the main case, at low temperature what will happen? This is the aim of Einstein's theory. So in order to find out the specific capacity behavior at low temperature, Einstein introduced a new temperature called Einstein's temperature, represented by theta E. Therefore, h nu is equal to k theta instead of t, kt, h nu by kt, where h nu is equal to kt, that instead of t, you substitute theta e. Okay, so h nu is equal to k theta e. Now, substitute this value in equation 12, you get this equation finally. So, Fe theta e by t e power theta e by t divided by e power theta e by t minus 1. So now you substitute the value of theta in that positions and you will get the low temperature values according to Einstein's theory. Are you understand? So in classical mechanics, there is only high temperature specific heat capacity is there, approach is there. But in low temperature, what will be the behavior of specific heat capacity? We don't know. That's why a new theory was introduced called Einstein's theory. So in Einstein's theory, he introduced a temperature called Einstein's temperature at low temperature. It is represented by theta E, and in the equation 12 he substituted, and we will get this final solution. Now, the Einstein's function determines the ratio of specific heat capacity at temperature T and the classical value of R. The Einstein's function determines, Einstein's function is nothing but f of e. This Einstein's function determines the ratio of specific heat capacity at temperature T and the classical value of 3R. I think in the earlier equation, Fe equal to, you make that Fe is equal to. Okay, so Fe gives the ratio between the specific temperature T and the classical value 3R. So what happens here? Einstein function I shown in the figure. What will be the figure here? I missed the figure. You see, when you draw a graph between the specific heat capacity and theta E, when you draw a graph between CV and theta E, when you draw a graph between CV and theta E, as the temperature goes on increases, it reaches a maximum value, and it is the higher temperature. Afterwards, it fell down rapidly. This happens in low temperature. Here, from 0, it will goes like this. It will reaches a maximum value, and it maintains at 3R level. This will be 3R. It maintains at the 3R level. After that, it will fall rapidly at low temperature. So this happens in the specific heat capacity based on Einstein's theory at low temperature. So at low temperature, the rate of fall of CV is more rapid. At low temperature, the rate of fall of CV is more rapid in this model. This discrepancy, why this happens? It is due to the assumption that all atoms vibrate with the same frequency independent of each other. We already made an assumption that all the atoms are vibrating with the same frequency and all are independent of each other. Each will vibrate its own time and its own energy, its own direction. Therefore, all vibrates with the same frequency but independent of each other. That's why when it reaches the higher temperature, at low temperature, it falls down rapidly. To avoid this discrepancy, a new model was introduced by Debye. Okay, now you understand why Debye's theory and why Einstein's theory came. In order to explain the low temperature behavior, Einstein's theory was introduced, then classical approach made by Dulong and Petit's law. When at the low temperature, the specific capacity falls rapidly because Einstein made the assumption that all the atoms vibrate with same frequency and independent of each other. In order to overcome this rapid fall of specific heat capacity, a new theory was introduced by Debye, and he made some assumptions. So what are the assumptions he made and how we derive the Debye's equation? In the next class we will discuss all the things. Okay, so in this class we studied about specific capacity, Dulong and Petit's law. According to Dulong and Petit's law, what will be the classical approach of specific capacity? Then Einstein's theory of specific capacity in order to explain the low temperature behavior of specific heat. Okay, so I understand you may follow the things and you just see the notes and you do it yourself, these calculations. And if you have any doubt, please ask me in WhatsApp or a Google Classroom. Till now nobody asked me any questions, so from that I conclude that you may understand. If you have any doubts, you raise your questions. Okay, we will meet in the next class with d by c theory. Okay, thank you, have a nice day, be safe.